Okay, so we are back with Rutherford and the discovery of the nucleus. So does so this is obviously partially about history and partially about historiography, which is how history gets recorded. So why doesn't somebody say what, as based on these readings, what actually happened? What was the actual sequence of events in the discovery of the nucleus? Does anyone want to volunteer?
Yeah, I'll have a go.
Okay.
Well, it, as far as I can remember, actually, it's a while since I did the reading, but my memory isn't as good as it was. It felt like it was the existing model at the time was this idea that everything was a sort of distributed cloud of charge, and then there started to be experiments showing that there was scattering which couldn't be accounted for. And what didn't happen was Rutherford doing an experiment, which is what I was taught, to ex demonstrate that his theory as to how that scattering was happening was true. It's somebody else that did that first. Then he did a theory, then he created a theory, and then that was um, shown by, I think, Geiger um, to be correct. Is that right?
Basically, that's what we're getting. Let me just um, I thought it was really fascinating that and you know this was news to me, um, that Gamow, Gamow, who was obviously an expert in the field, also got it wrong. So, well, does anyone want to say what uh, the reading in the book describes as the sequence of events instead? Which is more or less coincident, I think, with what all of us learned in school.
Well, I guess there was the Thompson, I guess this is like 1906 or something, and there was the Thompson understanding of the atomic structure, which made it seem like the atom was more kind of like a diffuse, uh, homogeneous structure. But then when they were doing these, um, I forget who was doing them. Maybe Rutherford was doing the experiments of this, like the gold foil, where it was just shooting the alpha. There was like this understanding of the alpha and beta particles, right? And the alpha particles are really big and heavy, and the beta particles were small and um, more likely to like bounce off things. But I guess they were noticing that the alpha particles were getting deflected um, more regularly than they would expect. And I guess the big kind of like thing that made the Thomson model kind of unfeasible was that sometimes the particles would bounce like backwards, like greater than 90 degrees off of the atom, or like off the atomic structure, which
Right.
seemed really unlikely.
So what's the big difference between in the article by I guess his name was Leone, Robati, and Verna, the experiment that never was. What's the big difference between the actual sequence of events as documented by the papers and the what you would call the canonical or standard history, which is echoed in Gamow's book, even though Gamow was a,
Was it that like there
expert.
wasn't this kind of like idealized Rutherford experiment, which like showed the exact structure of the nucleus? It was more kind of like a series of like 3 or 4 different like
So I guess
theory
it's whether the
experiment,
theory
theory
came first or
experiment.
the experimental came first.
Yeah.
What did you say?
So whether it was experimental results that led to the theory or the other way around.
That it was, I mean, it seems to me that the description of the actual events was much more an interaction between the theory, the development of theory, and the observations, right? In other words, as I see the story, which again is new to me, but I mean, given the references in the secondary account, I have no reason to challenge it. It seems perfectly accurate. Is that, the start is Rutherford looking for ways to experimentally probe the structure of the atom. J.J. Thomson, right, who had enormous prestige because he was the discoverer of the electron, which we've been over in earlier classes. So here he had this first shocking discovery that there was something smaller than the atom, much smaller, right? In terms of mass, 1,800 times smaller than the atom, not a small difference. So he had posited this, what was later termed, there I go again.
Bye.
And there's Peter.
All right. The computer has decided the globe is more interesting than I am.
It doesn't like what you're talking about.
Right. Well, listen, we'll get to that point. Can't you see it? The AI sensor that they build into all the computers. So yeah, and that's the other thing is computers are good at distracting you from what you're saying. So this is the model that was later called plum pudding. And I don't know whether Thomson came up with this name or later historians, but it's very descriptive, is an even distribution of these tiny negative charge carriers floating in a dispersed sea of positive charge. So it sort of makes intuitive sense because we're again talking about an atom whose density is not very different from the density of ordinary matter. But, Rutherford wanted to test this. And since the alpha particle had been recently discovered through the studies of radioactivity, he figured, well, this heavy particle, and of course they were able to measure these particle masses in the same way as the electron by crossing electric and magnetic fields. This massive particle, which would be deflected only slightly, would be a good probe. It would be able to get through the much lighter electrons and probe their distribution. So this is, probably the first instance of the basic concept of probing the structure of the nucleus of the atom and below with accelerated particles. Now, he wasn't doing the acceleration. The acceleration was provided by the energy of the radioactive decay, but it was the same thing. So he collimated the isotropic emission of these alphas with a little diaphragm. So he got geometrically a beam and then put that collimated beam onto the foil. But what was interesting is the sequence of events, right? Initially, what he saw was some scattering. It was a surprising amount of scattering considering J.J. Thomson's model. But it wasn't this high angle scatter, and it certainly wasn't backscatter, which was in the, what we can now say, the mythical version of the discovery. So that set in motion these additional experiments, each experiment basically being more sensitive because they went from photographic to these scintillators and extending to higher and higher angles. Initially, they had no reason to do because there was no expectation. So that's the second question I'll ask. Why was there no expectation? Because Thomson himself said that there could be multiple scatterings. So why was there no expectation that these multiple scatterings could lead to large angles? Did people follow the...
Yeah, I guess it would be because if something was scattering.
Let me ask. All right, you've responded, so let me ask, can somebody else respond?
Because Thomson, this is Martin, Thomson's, I call it the sponge model. Atomic model was like a sponge with the space filled and distributed matter through all of it. And that could not account for 90-degree or 180-degree scattering of alpha particles. Because for that to happen, you need a large concentration of mass to affect the trajectory of the alpha particle. But the sponge model that Thomson developed didn't account for that. I mean, it couldn't actually generate that type of behavior in the trajectory of the alpha particles going through the atoms.
But what I'm asking is, just briefly, mathematically, why couldn't you get the large angle scattering by J.J. Thomson's suggestion that there could be multiple scattering within the foil?
Because the alpha particle has a large kinetic energy, and so you need to impart a significant amount of energy to change the direction of the movement of alpha particle. And for that, you need a higher concentration of mass that is not moving.
Well, there's an additional reason. Does anybody else want to comment?
It would be statistical, wouldn't it? You'd be scattering, and multiple scattering would tend to average out.
The problem was that the probability, there is a probability of getting multiple scattering, but the probability of those scatterings building up to a very large angle was, was infinitesimal. And you can sort of see this because it's like a random walk. In other words, if you have a small angle scattering, and by the way, in plasmas, most of the scattering is small angle scattering. The large angle scattering is not insignificant, but relatively smaller. So if you have a small angle scattering, then the next scattering, of course, can either increase that angle or decrease it. It's a random walk. So the number of steps to increase the angle by a set amount actually increases as the square of that amount. So to get from the small angle of a degree or less up to 90 degrees that was observed, you get an exponential explosion of the number of scattering that's needed. And that, of course, as Rutherford later explained in his paper, completely ruled out multiple scatterings. These large angle scatterings had to be the result of a single encounter.
So that would be like conditional probability, the probability of having enough sequential small degree changes to add up to 90 degrees or even 180 when it just went back is astronomically low.
That's right. I mean, it's exponential.
Yeah.
The drop off is exponential. And of course, so, okay, so, I mean, so basically we have this sequence of increasing, somebody wanted to get in? No. We had this sequence of increasingly sensitive experiments, initially with Rutherford and then with his students, Geiger and who was the other guy?
Marsden.
Geiger and Marsden.
Marsden.
Yeah.
Right. And then we have the real historical breakthrough, which is the 1911 paper by Rutherford. So does anyone want, does anyone want to elaborate on, I mean, the main point is obviously what we've already described. That Rutherford points out that it is impossible to get these large angle scattering that has been documented over these 5 years of experiments without postulating a very heavy concentration of mass in the nucleus, in the atom. So what else does he conclude from this? And what else well, let me just be open-ended. What else did people get out of this Rutherford's paper, and whether there was things that they didn't understand about the argument? Either one.
This is Elliot. I just wanted to say that it seems to me I was questioning the role of the theoretician versus the experimenter here, and it seems like Rutherford, as a theoretician, initially did some experiments, but he was focused on posing problems, asking the right questions, and then leaving the elaboration of the experiments to others more proficient in the lab. And then later on, with more results, he gradually formulated a new theory that then could be further tested and formulated, I guess, in a form that could be easily verified or refuted. And so it's not, the theoretician doesn't just propose theories out of the blue, out of his head. He actually asks questions that then need to be explored. And then he's more adept maybe than some pure experimenters at formulating that into a new conception that I think is the basis for these breakthroughs.
I think, Eric, what you might be getting at is a note that the angle of deflections are related to the atomic weight. That was one of the key takeaways from Geiger's work. And it was there that Rutherford began to make those correlations, particularly through electric fields. I sort of am obscure. It's obscure to me how all those connections come together, but those were the points that he was trying to connect.
Yeah, that's one thing, is that he started, it was not only in this paper that he said there is a heavy nucleus. He started to quantify this theory in a way that it could be tested by subsequent experiments. And of course, one of the things that's exciting when you read these papers is you see the very different pace at which science was advancing a century ago. Is that as this paper was being written, the experiments to test his theory were being done. So he actually refers to those experiments in this paper saying, oh yeah, they're going to publish these experiments shortly. So yeah, that's one big thing that is quantified, is the correlation of the scattering with the square of the atomic charge. To get back to your comments, Elliot, I mean, I think what you can say historically is that in 1911, you don't yet really see the clear self-identification, you might say, of physicists as theoreticians or experimentalists. That is something that's actually really going to come in the course of the next quarter century or so. So I doubt whether Rutherford would have characterized himself as a theoretician or as an experimentalist. He was a physicist, and in those days, most physicists did both. Now, we know, obviously, that we have, the example of Einstein, who was purely a theoretician, but even, this is 6 years after Einstein's big discoveries in relativity and the photoelectric effect. And the vast majority, I would say, the vast majority of physicists are people who routinely do both theory and experiment. So I doubt whether he's consciously leaving things he's consciously leaving the experiments to others. Obviously, what happened was that his students took these experiments further than he was able to. And I think that that's something that, good students are expected to do, good, graduate level students. So I think that was what was happening, was he was expecting that people would take these experiments further. Not that he was not an experimentalist, but that others would continue this work. So
nonetheless, wouldn't you say that after the fact, the way this experiment was idealized paints him as the theoretical, eminence who gets the historical credit for everything, and the students are kind of left in the background?
that's
And
right.
so, in fact, both in terms of the actual behavior that was evidenced by this collaborative set of physicists, the
Right.
behavior itself evidenced this emerging schism. And on top of that, it was exploited in order to feed this notion of this idealized science where there were these truths, and these geniuses discovered these eternal truths and
Right.
locked them down for posterity.
Yeah. Right. I think that
pantheon of heads, these pantheon of genial heads, and collaborators are left in the background, sort of hidden.
I mean, we see this, the great man theory in these higher, and both words are significant. The great man theory of history in general, that, Napoleon and Stalin and Hitler and so on, that it was these individuals, for good or for evil, that shape history, that ideological reflection of general individualist ideology, of course, is what drives a lot of this mythology, in which we have, the Einstein being the sort of poster boy for this mythology. But again, Rutherford, and we see it, again and again, in which the collaborators are left out, and especially when, and is not as the case in this particular example, when the collaborations are women, they are especially likely to be left out. I don't know whether, I forget what stories I've shared with you people as opposed to others, but did I mention the case of my own professor at Columbia? Did I talk about her? Okay. Well, this is a very appropriate example. So I think it was last year, I saw a woman on the cover of Physics Today, and she looked vaguely familiar. And sure enough, when I opened it, it was a story about Dr. Wu. And Dr. Wu was my lab professor at Columbia. Now, the theoretical prejudice of physics was already so high by the time I was in school in the 1960s that I had precisely one lab course in getting my degree in physics from Columbia University. And that was my senior year, and she taught it. It was a great course. For one thing, it was one-on-one. It was designed so there was only one senior student per lab session with her. And she was just a great teacher. So the story was about the fact that she was the theoretician who predicted the violation of parity. So the violation of the geometric symmetry of elementary particles, that particles tend to have handedness like screws, and their spins tend to be aligned with their motion or counter-aligned. But the Nobel Prize went to the two experimentalists, one of whom was also teaching at Columbia, T.D. Lee, who confirmed this theoretical prediction. And she was not honored with a Nobel Prize, which was again, characteristic. It was in opposition to the normal narrative of honoring the theoretician more than the experimentalist, but very much in accord with the tradition of honoring the males and not the females. So I was curious. Now, at the time, people had said of Dr. Wu that she was the only full professor, female full professor in the physics department at the time. And my fellow students said, oh yeah, they have her teaching the lab because nobody wants to, so they assigned it to the woman. So I got curious, and I went to the website of my alma mater and I looked up the physics department, and I counted the number of full professors, because they have their pictures on the website, who were women. And I will give only one guess as to how many women are currently on the faculty of the Columbia University Physics Department. Anyone? You want to make a guess?
One.
One. I think I told you the story, Sam. That's cheating. But anyway, yes, of course, the answer is, 60 years later, no progress has been made, and there's one teacher, and of course, guess what course she's teaching? Laboratory. Our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy and a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks. So, so obviously, to come back to our example, the lesson, the historiography lesson of this is exactly what you were saying. The influence of the great man theory of progress of history into scientific history, where it really distorts the history, but even more, I think it really discourages people, because it basically says either you are going to be one of these geniuses, of which there are only, one or two each decade, or you're not really contributing to the advance of the science, which, as this example shows in miniature, is simply not the way science advances. Science is a collaborative enterprise. Yes, go ahead.
I was
Peter.
just thinking, just going back to the beginning of this, when they were firing alpha particles at air to start with, and then they started using these thin gold targets and everything. Presumably at that point, they would have assumed that if the target was thick enough, the alpha particles would just be absorbed. So they probably weren't even expecting transmission or reflection, anything. They were just expecting them to be absorbed in the process, would they?
Well, no, Rutherford was expecting something. I mean, he was using these particles, these heavy particles, because he was testing the Thomson hypothesis. Now, Thomson was a very, as I say, by that time, a very prestigious scientist. So with that hypothesis, you would expect some deflection.
Right. Okay.
Because the diffuse positive mass would be able to deflect the helium. Because remember, we're talking about air, so you've got mainly nitrogen and oxygen. So nitrogen and oxygen was well known by that time, were heavier atoms than the alpha particle, which by that time I think was known to be the nucleus of a helium atom. Well, I'm not sure, but its mass was known. So you would expect, even if the mass was diffuse, a measurable deflection. So that's what they were expecting, and that's what they got. But what they got was, it was more easily measurable. And it was, as we saw from the images, it was obvious at a glance. It wasn't something that needed, precise measurement. It was obvious at a glance that there was significant scattering when you compared air with a vacuum. It wasn't subtle. So that's what motivated the sequence of experiments in which, by increasing in sensitivity, they would continue to move outward in angle. So to get back to the quantitative aspects, so one aspect was the correlation with Z. What was another quantitative aspect? Which was, what was another quantitative aspect that Rutherford derived in this paper?
Well, presumably the thickness of the target, would it?
Well, here, first of all, again, I'm asking other people who haven't spoken on. Robert, Brian? All right. Well, the thickness of the target, yes. But what about the details of the hypothesis?
That the scattering, that was in 1911, that the scattering, his hypothesized that the scattering was based on the assumption that the large angle of scattering are due to a single atomic collision. That's what he posited that in 1911.
Right. So that was basically the key evidence that there was a concentration of mass. But he went further. All right. Well, the key thing that I'm asking for is, he basically derived approximately how big that concentrated mass was compared with the atom.
The nuclear radius.
Right. Do people remember how he did that?
No.
Anybody?
Passed it through a tube on one of his experiments. And I was wondering, why was it these different metals, of about a dozen, that he used to show the results of all the different metals? But one of his experiments was passing it through a glass tube that was lined with the reflective gold, or maybe it was. And another one was where he passed, well, first was, maybe that was the scintillations passing through a slit and then onto something like photographic paper or something. And then there was the thickness of the gold, whether it was one sheaf of gold or two. And then there was these measurements with the different metals. and they all had kind of similar or uniform results, maybe with the different metals. I don't know if that's what I remember was but there were several different mentioned in it of these ways of doing that measuring.
Right. But I guess again, I'm not sure that the mathematics is sufficiently clear. I was asking, like, basically, what calculation led him to the conclusion that the nucleus was as small as it actually is, which is orders of magnitude smaller than the radius of the atom.
Well, the angle of the deflections were so extreme. Of some that were measured, they were so extreme they couldn't account for it otherwise.
Right, but I mean, why he concluded here on page 671 of the article that the radius is something of the order of 10 to the minus
4.
These are new contact lenses, and I'm not sure that
It's 10 to the minus 19 versus 10 to the minus 23. There's 10 to the minus 4 difference.
13.
Is it?
10 to the minus. Well, people look in 671. At the bottom of 671, it's 10 to the minus 12, I guess. At the bottom of the page.
Yeah.
10 to the minus
3.
8th. 10 to the minus
Wait,
eighth.
but there's several.
The velocity of 2 times 10 to the 9 centimeters per second is about 3.4 times 10 to the minus 12 centimeters. Am I reading that correctly?
Yes, that's correct.
Yeah.
Yeah.
All right. So we can see here the answer, I've sort of pointed to it, is that if you have a point particle, if you assume something is not a point, but a spherical distribution of charge, which can be calculated equivalent to a point, there's a simple relationship between the speed of the particle that you're using to probe and the deflection. So since he knew the speed of the alpha particles, you can calculate how close they have to be to a charge of a given magnitude. And he knew the charge. They'd known for decades what the charge on the, what the elementary charge was. And you can calculate how close you have to get for a given deflection. So do people see that? In other words, if it's deflected, if it's a head-on, if it's heading towards the particle directly, right, then it's going to get to a certain point where it can't get any closer because that's the distribution of the charge. So you can calculate for a given speed how close that has to be for a given deflection. So since he knew the speed, he knew the charge, he could calculate what was the radius, and this is an upper limit. In other words, the nucleus could be smaller than this. he could see what was the radius directly from the calculation that he does on page 671. So that's how he arrived at what must have been an extremely startling conclusion. We're talking about a nucleus that is at least 10 to the 4th times, 10,000 times smaller in radius than the atom. And that meant 10 to the 12th times smaller in volume. So all of a sudden, you have this incredible idea that the mass of the atoms, the mass of everything that we're composed of, that the whole world is composed of, is concentrated at this enormous density, trillions of times more than the density of solid matter. And then most obviously, conversely, then most of the space in an atom is empty. So I see a hand up. Yes, Ron.
Yeah, I mean, nobody seems to want to tackle the contradiction of this, because what you've got is you've got electrons and protons, which are highly charged. Initially, you're saying, okay, they're diffuse, so they're spread over a wider area, so the distance between these charged points is going to be bigger, therefore less force involved to bring them close. But now you're putting them even smaller, closer and closer together. How are you overcoming the repulsive forces between the charged particles? And even Thomson, I think, says somewhere that, oh, this is a problem for later, but nobody gets back to it. We call it the strong force, but there is no explanation for it. It's just the name.
Right. Well, that's an excellent point, which is we will see going forward that the enormous progress that was rapidly made over this period, and which continues into the 1930s, of basically interpreting phenomena in terms of smaller and smaller phenomena, basically hit a wall. And even though that general paradigm continued, because of course any particle physicist will tell you, well, we know that nucleons are composed of quarks. Later in this class, we'll get into all the problems with that hypothesis. They're not as profound as the problems with the Big Bang hypothesis, but they are pretty profound. So Rutherford already saw one problem with his model and immediately pushed it off to the future, which is that if you have a solar system sort of model in which so we've gone from plum pudding, which clearly can be an equilibrium static solution, right? In other words, we see this in crystals. So you could have electrons motionless within this diffuse positive charge distribution. So Thomson's model was static and in equilibrium. Rutherford immediately saw that his model wasn't, that the electrons would have to be moving at pretty high velocity around the nucleus to create the observed 10 to the minus 8 centimeter radius of the atom. So we could easily calculate, what velocity they'd have to be moving to maintain that orbit. And he knew from the developments in electromagnetism over the last 50 years that an electron accelerating that fast, going around in whatever it was, 10 to the minus 14 seconds, would radiate energy. And that radiation of energy, right? Any moving charge radiates energy. And that radiation of energy would cause the atom, his atomic model, to be unstable on time periods of something like 10 to the minus 8 seconds. So he recognizes that and immediately says, well, I'm not talking about that right now. And that was very good. That was a good decision. I mean, again, to jump to my other interest, the cosmologists always say, well, if you want to replace our model, you have to have a complete model that explains everything. And if Rutherford had taken that, well, I'd better wait to publish this until I can explain the stability of the atom, he wouldn't have published. Now, that particular problem is resolved in the coming decades with the development of quantum theory. But he takes the step to say, look, this is what the data shows. Theoretically, we can't fully understand it because we know atoms are not only stable, they're incredibly stable. But he says, this is what the data shows, that the nucleus has to be, this small. And since we already know that the electrons are individual particles, so at that time, they're not knowledgeable of the wave nature of matter, there's this theoretical contradiction, but we put this aside. There has to be an explanation for it because this is what the data shows. Comments, questions on this part?
My question was, what was the purpose of these measurements with the different, I think it was about a dozen different metals? What was the purpose to show there, or any conclusion from that?
Anybody want to answer that? Why was he testing different metals, materials?
Well, wouldn't it just give him different data points for atoms that have different atomic numbers?
Right. Right. He would.
So you could test against various potential sizes of the.
Right. If we
mass.
go back to Coulomb's law, which is what he was using, if you have the interaction of a charged particle with another charged particle, what enters into that equation is the charge on each particle. So he wanted to vary the charge on the particles. And the only way you can do that, he couldn't vary the charge on the incoming particle because all he had was alphas. So he would vary the charge on the stationary particle by varying the material. And if you look on page 681, he has the analysis of this. Now, what he knew, now it's interesting to separate what we know from what he knew. We know that the atomic charge on the nucleus is simply is equal to the number of electrons in the atom. So each atom, neutral atom, has the same number of electrons as protons. But remember, at this time, he was just discovering the existence of the nucleus. So what he knew from chemistry was the atomic mass, which, of course, he's hypothesizing that the mass of the nucleus is the greater, by far the greater proportion of the mass of the atom. So what he does is he takes the atomic weight, or atomic mass in our current terminology, of these various metals. So they had to be a metal because that's what they were able to coat on the glass. And he calculated theoretically, again, just based on Coulomb's law, that the number of particles deflected would be proportional to the charge to the 3/2 power. So on page 681, he makes the assumption, which we know to be approximately accurate, not completely, that the charge and the mass are proportional. Now, we know, as I say today, that the mass is almost proportional to the number of protons plus the number of neutrons. And since the number of neutrons grows faster than the number of protons as we go up the periodical table, there's not an exact one-to-one relationship between the atomic charge and the atomic mass, but it's actually pretty close. So what he compares here is the prediction of the number of particles scattered, which is he designates as Z, in the central column of the table on page 681, and the A to the 3/2 scaling. So we got the atomic weight, A, in the first column, the number of particles observed in the second column, and I assume this is per shot, it's an average per observation because we see we have fractional values. And then he compares that with what he expects to be constant, which is that Z should be proportional to A to the 3/2. And he shows that it's pretty close. So in this way, he basically was confirming that all the positive charge is concentrated in this tiny nucleus. And again, this is really, when you look at it, it's a really shocking discovery, because instead of saying that the average density of the negative and positive charges within the atom was about the same, he's saying that there's this tremendous contrast in the charge density of the electrons, which he's now hypothesizing are relatively evenly spaced within the atom, and the positive charges that are in this tiny nucleus, 1 trillion times smaller. And of course, the mass density between the mass that's carrying the positive charge, which we now know are protons, and the mass carried by the negative charges is even bigger, because the electrons are only each carrying 1/1800th of the mass of the atom. approximately 1/3000th, counting the neutrons. So you've got now a 10 to the 15th contrast in the mass density of the negative charge carriers and the mass density of the positive charge carriers. And, you know, I mean, this is the first real instance in which science, physics comes up. And this happens more as we go into the 20th century with these gigantic numbers. That where do they come from? Where does this enormous contrast in mass density come from? And I was trying to think of a way of illustrating 10 to the 15th. So this is approximately taking the island of Manhattan, including its bedrock down 10 kilometers, and compressing it into a size of a marble. That's about the density contrast that we're talking about, of the difference between the density of a nucleus and the density of ordinary matter, such as the rock that Manhattan skyscrapers rest on. Our videos come out of LPPFusion's research in fusion energy, which will power a future with abundance for all, with a clean, sustainable economy and environment. Goods, housing, and infrastructure would be extremely affordable once fusion kicks in. Fusion energy is the key to an advanced future. Support fusion research. The link's in the description, and thanks. I guess what I'd like to ask is, at some point in your education, all of you must have learned this fact. I mean, what do you make of it? What is your reaction to it initially, and what's your reaction to it now?
Shocking.
What?
Shocking. Were people freaking out at the time?
I was asking myself that question. I think that would be something would be interesting to research for the next class, what the reaction to Rutherford's paper was. I mean, I know that everybody did react, that everybody saw that the electrodynamic problem of the model, that it would collapse and all the energy would be radiated away. And that's what we'll get into in the next.
But there wasn't a body of people saying this can't be right, was there? Because it was shown that it had to be right.
As I say, I don't know whether that was the reaction. I mean,
it did say one of, I don't know if it was the first, I think it was probably the second paper, the more recent one, but kind of towards the end stated that it semi, I don't know how quick it happened, but it did become like just the accepted model across the board, which is kind of interesting to observe, like over a period of 5 years. And I guess we've been discussing in this group how that used to happen more like in the earlier half of last century, like just kind of our physical understanding of the universe, like so quickly shifting to a new model.
right. Certainly, as I say, I can't say exactly what the reaction was to Rutherford's model. We definitely will get into that because, as I say, Bohr's atom was a reaction to try to solve the problem of the lack of radiation from the atom by applying the quantum hypothesis to the atom. So we'll get into what the reaction was, but I certainly agree that what we can see from the papers was there was a much greater openness a century ago to major changes in the paradigm. What you see today is an openness, an excessive openness to new hypotheses that build on the existing paradigm, especially in cosmology. I mean, particle physics has evolved to the point where I think there is, like in the famous case of Sabine Hassenfelder, I think there is much more general skepticism about new theoretical concepts that have no basis in experiment. But in cosmology, we see, oh, there's new theoretical discoveries all the time, but it's very much building on the existing paradigm. And people are all familiar with my and my colleagues' problems with, or the data's problems with that paradigm. So a century ago, empirically, there certainly was a much greater openness to say, we don't really know what the basic paradigm is, and that can shift very quickly. So it'll be interesting, maybe we should discuss this some next time, to look at some of the sociological reasons why that was true then and is arguably much less true today.
I have to confess that I've just asked ChatGPT that very question.
Oh my God.
I shouldn't. It basically says what we just said. It says that the immediate reaction was surprise and skepticism, but within 2 years, everyone accepted it, basically.
Mm-hmm. 2 years.
2 years, basically, yeah.
Yeah.
I mean, I guess this is what we've talked about this too, but like the experiments were easier for some of this stuff. Like it was a lower barrier of entry, so you could have this kind of new theory and this new model, and then a bunch of people could try it themselves.
The experiments were certainly cheaper to conduct, but there definitely was I would say, and I guess it would take a big historical project to prove this, but I would say that the funds per physicist were more abundant. I mean, LPPFusion is doing a relatively cheap experiment now.
Right.
Certainly our equipment is not as cheap as the equipment needed for the Rutherford and Geiger experiments. That would be, certainly an order of magnitude cheaper, more than an order of magnitude cheaper. But, we do feel that we're doing cutting edge research with a team of 4 people, which was certainly not an unusual size team for back then. And then as now, the principal cost was not the equipment, but paying people's salaries. So I would not say that today, in terms of, person hours or person years, experiments that can change paradigms are that much more expensive. In cosmology, it's true. These instruments are hugely expensive to build, but that is still considered a state responsibility, a government responsibility. Researchers don't pay for JWST. They don't pay to use JWST. with some delays, all of that data becomes freely available. And in fact, I and my colleagues do cosmology research on essentially no resources except our own time. So I think that we have to, look elsewhere than the cost of equipment for the change in the what you might call the flexibility of thinking in physics. And I think it comes down to that today there is far more competition for the resources that were on a per person. I mean, the amount of resources collectively is much bigger today than it is then. But on a per person basis, a per physicist basis, I would argue that it's a good deal smaller. In terms of my own personal research, when I was still working mainly as a journalist in science journalism in the 90s, I did report on a number of studies that showed that with the end of the Cold War, the support for physics per physicist dropped rapidly by 50%. And it's never recovered since. And that was reflected, for example, in other statistics of the number of grant applications per, per grant. So I think that today there's a much more competitive environment for resources in physics than there was 100 and odd years ago.
But isn't there a concentration of control of resources, largely committees set up in the National Science Foundation, places like that, that you get, or Department of Energy, that you get sort of ossified, kind of incestuous committees that just pal review each other and hand out grants to each other, and
Yes,
then
absolutely.
dogmatic.
Yes, I certainly think that that's the other part of the equation. And I basically, I don't know whether I've published this anywhere. I have put out that essentially orthodoxy infects the parts of science where two conditions are true, that there's a lot of competition for resources and there's a lot of concentration in the allocation of those resources. If you don't have those conditions, both of those conditions true, you have less incentive for orthodoxy and more for flexibility. Because even if you're in a competitive environment, if you can shop your proposal to many centers, then you can still do the research. Obviously, the big change was the change to government-financed research after the Second World War, which was pioneered by the American government. So initially, that had a beneficial effect of actually making more resources available, specifically to the physical sciences and eventually to the biological sciences as the decades progressed. But in certain fields, not all fields, it had the negative consequence that you had very few suppliers. And certainly in certain fields of physics, which is fundamental or particle physics and cosmology, you have the reduction ad absurdum, in which you have one or two committees being responsible for this whole field. And those are the fields that are, most ossified. And as you go to other fields like solid state research, where there are more sources of funding, you generally have, more flexibility. But we should continue. We're
Good
pretty much
investors will-
should continue this aspect, very important aspect of the sociology of science and how it starts to change during the course of the 20th century. We'll continue next time. So we are going to go on to the Bohr atom, and but the readings do cover that. And I'll have to let you all know when is reasonable, but I hope that we will be able to do this in about a month's time. We do have, I'm going to announce this generally, but for people in the New York metropolitan area, we are going to have our first, maybe our first post-pandemic big in-person event in New York City next month. It's going to be on November 13th, and it will be a sort of update overview of the situation in cosmology. So if you are in the metropolitan area or likely to be there in the area of November 13th, we'll be announcing that event within days. So any last comments?
Yes, it seems I can see where understanding the structure of the atom is actually critical to understanding cosmology. There's a definite connection there that's obvious to me.
Right. And obviously this connection has grown up over the decades. I think that, you know, that's one point on which all sides will agree, is that there is a strong connection between the microscopic and the supermacroscopic. What that connection is, obviously, is a matter of dispute. But I think a key significance of this class, or the subject matter of this class, is that this is sort of the first step at which we've gotten to see problems that haven't been fully resolved in, you know, the rather long time, the century plus a decade, 110 years. And obviously the question that was raised of how does the charge in the nucleus, and we're basically saying now today, the charge in the proton, stay together? And that's a very interesting question, for which I think there has been some progress made in recent years, but we'll return to it many times in the coming classes. So with that, I'll say, yes, we're out of time, and I hope everybody will come back. Speaking of gender differentials in physics, I noticed we don't have our female component, so I hope they'll be able to come back next month. Okay, everybody take care then. Have a good.
Thanks very much, Eric.
Thanks, Eric. Take care.
Bye.
Bye, everyone.
Everyone.
Bye.